Earth Systems 3209, Unit 2, Historical Geology. References for this presentation can be seen in Chapters 6, Chapters 8, Appendix A, and Appendix B. Unit 2, Topic 2.4, Absolute Time and Radioactivity. The focus of this presentation will be on defining terminology related to radioactivity and describing the relationship between half-life, parent, and daughter isotopes. Text references can be seen on pages 228 and 235 in your textbook. Terminology related to radioactivity involves defining the term isotope. Isotopes are variations of an element that have different mass numbers. Different elements would have different isotopes. Some of these isotopes are stable, and some of these isotopes are radioactive. The radioactive isotopes are the elements that are used to determine the age of rocks that date back billions of years. Radioactive elements are unstable in nature and give off radiation as they undergo radioactive decay to form stable daughter products. Radioactive elements decay at a constant rate and are thought to start decaying as soon as the rock is formed. This is important when we look at igneous rocks, which do contain a lot of radioactive isotopes. As soon as the magma crystallizes, the radioactive isotopes in the newly formed rock will start to decay. And this decaying of radioactive isotopes and comparing to the stable daughter product that's being produced is a hint and can be used to determine the age of the igneous rocks. One dating method that is used commonly when looking at igneous rocks is uranium-238 decaying to form the isotope lead-206. This is a very common isotope used to date igneous rocks. Looking at the diagram to the right, we can see that uranium-238 undergoes 14 different decay processes in becoming a stable daughter product. Once it reaches the 14th decay process, it forms a stable isotope of lead-206. With each decay, energy is given off, and this energy is stored in rocks. The term radioactivity describes a process where unstable isotopes will emit energy to achieve stability. The rate at which the radioactive elements decay is referred to as its half-life. This terminology will be used when we look at calculating the radioactive dates of different isotopes. The half-life is the time it takes for one half of an unstable isotope to decay to form a stable isotope. So in the previous example of uranium-238 decaying to lead-206, it would be the time it takes for a sample of uranium-238 to decay to one half its size, so it produces 50% daughter material, which is stable, and that would be the lead-206, and 50% of the remaining radioactive isotope, uranium-238, would remain. So if we look at the graph, which is called a decay graph below, we'll see that 100% of the material, the radioactive isotope, is present in the rock when the rock first forms. After one half-life, 50% of the radioactive isotope will decay. Therefore, you now have 50 atoms of the radioactive isotope and 50 atoms of the stable daughter isotope. After a second half-life, half of the 50% of the radioactive material remaining will decay. Now we have only 25% of the radioactive isotope remaining, and we have 75% of the stable daughter product remaining. Once the sample undergoes a third radioactive decay, now we have 12.5% of the parent isotope remaining and 87.5% of the daughter product remaining. This process will continue until all of the parent material has decayed. Some other common terminology related to radioactivity involves or includes parent elements. The parent element is the unstable radioactive material. When the unstable radioactive parent material breaks down, it will form a stable decay product called the daughter material. When we add both the parent material and the daughter material together, both will add up to be 100%. Therefore, the ratio of the amount of unstable parent material to the amount of the stable daughter material can be used to determine absolute age of a rock. Several different dating methods can be used to find the age of different rocks. Some of these dating methods and corresponding half-lives are listed below. For example, uranium-238 will decay to form lead-206. When uranium-238 decays to form stable lead-206, it takes 4.5 billion years for this half-life to occur. Example number 2, uranium-235 will decay to form lead-207. When this radioactive isotope decays, it takes 713 million years for a half-life to occur. Another common isotope, and used in a lot of igneous rocks, because igneous rocks would contain potassium feldspar, is the potassium-40 decays to argon-40 dating method. This method would take 1.31 billion years for half of the radioactive sample to decay. A fourth radioactive dating method used is carbon-14 decaying to form nitrogen-14. The half-life of carbon-14 decaying to form nitrogen-14 is only 5,730 years. This is a very small half-life and is commonly used to date once-living things or fossils of once-living remains that are found in rocks. A fifth dating method that can be used is rubidium-87 decaying to strontium-87. This dating method has a half-life of 47 billion years. Some limitations to using radioactive dating. When a radioactive sample decays to form a stable daughter product, if we have the addition or loss of any parent or daughter during the decay process, the results that are given can be false. Certain parent isotopes are only appropriate under certain conditions. For example, carbon-14 dates once-living organisms, and some isotopes have too long or too short a half-life to date certain materials. Where carbon-14's half-life is 5,730 years, it can only date back to approximately 1 million years old. Metamorphism also causes the radioactive clocks to reset, so if a rock becomes metamorphosed, the radioactive elements within that rock automatically gets reset and it starts to decay from that point. So in this case, we can use radioactive elements in a rock to date the process where metamorphism had occurred. Sedimentary rocks are formed from previously existing weathered and eroded rocks. Therefore, this can give different ages for different parts of a sedimentary rock sample. Some parts of a rock, some sediments, can be located in different age time zones, and therefore different particles within a conglomerate, for example, could have different age dates. So these are some of the limitations to using radioactive dating. Let's have a look at some examples of past public exam questions. First question reads, which radioactive isotope would be used to date the bones of an ancient mummy? If we're going to look at an ancient mummy, that would be a once living thing. Therefore, it would be relatively young in age compared to a lot of rocks that are found on the Earth. Seeing that it's relatively young, we would need a half-life that is relatively young, and carbon-14 has a half-life of 5,730 years, and it's also used to date once living things. So carbon-14 would be the most appropriate radioactive dating method to date an ancient mummy. Example number 2. What is the half-life in millions of years of the element represented in the graph below? In the radioactive decay graph we see here, on the y-axis we see the amount of parent material remaining in percentage, and on the x-axis we see time in millions of years. So if we're looking for what is the half-life in millions of years, one half-life will be the time it takes for 50% of the material to decay. So if we look at the amount of percent of material remaining as 50%, we can come over to our decay graph, and we notice that it intersects the plotted line at the 100 million year mark. So the half-life represented by this decay graph would be 100 million years. So the answer would be B. Your turn. Take the time to complete the following questions. You can stop your recording now and prepare your solution, and then resume your recording to find out the answer on the next slide. The solution to the question, why is carbon-14 not used to date rocks of Paleozoic age? And the answer is its half-life is too short. In summary, overview of the terminology associated with radioactivity. Radioactivity focuses or includes topics such as isotopes, half-life, radioactive decay, parent element, and daughter element. Also, the radioactive dating methods that can be used to date different radioactive samples are uranium-238 decaying to form lead-206, which has a half-life of 4.5 billion years. Uranium-235, which decays to form lead-207, which has a half-life of 713 million years. Potassium-40 decaying to form argon-40, which has a half-life of 1.31 billion years. And carbon-14 decaying to form nitrogen-14, which has a half-life of 5,730 years. And the last dating method we studied is rubidium-87 decaying to form strontium-87, which has a half